last class we discussed about 4 to 20 milliampere current transmitter, that was using a potentiometer. We had discussed. We had shown how to design a 420 milliampere current transmitter, and then we also explained how to calculate the various resistance values that is used in the circuit. Today we continue on that and explain how to do the error budgeting for the same 420 milliampere current transmitter. So, we will pick up the topic error budgeting for 420 milliampere current transmitter. Because as we discussed earlier, error budgeting is a very important aspect in analog circuit design. So, we do this error budgeting for this current transmitter. Now, first let us draw the current transmitter circuit first, then we pick up one error after another. So, here we have the voltage source, and then we had the regulator that consists of one Darlington pair transistor. This we had discussed in the previous class. So, we had the biasing resistance here, and then we had the output. So, output voltage is taken, and then we had the error amplifier for voltage regulator. So, we had the plus, then we had this, and then we have connected this. So, this is a current transmitter, voltage regulator part of the current transmitter is this. So, we had 470 K resistance here, and this is in order to give a startup current for that. Now, then we draw the other part of the circuit, that is the transmitter part, that is like this. We had this, and then we had this is connected to this, that is 0 part, then we had this, that when voltage increase they have to increase. So, we had this, then we also connected and this is connected to this. So, the second part is this is the second part is the current transmitter part, this is a voltage regulator part. So, this is a voltage regulator, this is a current transmitter part. So, typically we get 0 to say 7 volt here fixed, and if this 7 volt is determined by this V reference and these two resistance say R10 and R11. So, this R10, R11 and V reference actually forms this 7 volt, because we know voltage at this point is a 5 volt, then we want this is to be 5, and then across this is voltage across this is 5 volt. So, you can adjust R10 to get whatever voltage you want. Now, if we look at the error, basically if the V reference changes with temperature, then this 7 volt will change, because if this increases, obviously this point also have to follow that, and then this output also have to increase. Similarly, if this resistance and this resistance drifts, then also output voltage will change. So, if this regulator voltage changes, then voltage at this point will change. For a given position, you have kept the potentiometer point fixed. So, if this increases, then this also will increase, that will increase the current through this. So, first we have to calculate what is the error that is expected, maximum error expected due to change in the regulated voltage. If the regulated voltage changes, what will be the current error, that is what we have to calculate first. So, we take the zener, for example, if we have taken a take a typical zener, say LM 336 is used as a zener diode. Then if you look at the data sheet of LM 336, the zener 5 volt zener, the drift is given as 30 ppm per degree C. So, drift actually for zener is 30 ppm per degree C. So, what is the expected output voltage change? If the zener drifts by 30 ppm per degree C, then what is the output voltage change due to the zener drift? So, that means first we have to find out what is the voltage change at the zener end for 100 degree C, assuming ambient temperature as ambient temperature change equal to 100 degree C. This is required because if you are making industrial grade equipment and then it has to withstand minus 20 degree to plus 80 degree. So, the maximum temperature change expected is 100 degree C. So, we take 100 degree C as the temperature change. Then, so voltage, assuming voltage of the zener initially be 5 volt. So, delta V of the zener is equal to change in zener voltage, that will be 5 into 30 ppm, that is 10 power 6 into 100 degree C. Basically, it is V into ppm into T delta T, that is what we had shown in this. So, delta V then it becomes, that is 15 into 10 power 3 divided by 10 power 6, that is 15 into 10 power minus 3 volt, that is 15 millivolt. So, zener voltage will change by plus or minus 15 millivolt for 100 degree temperature change. So, the delta V of the zener, delta V of the zener is equal to plus or minus 15 millivolt. If zener voltage changes by 50 millivolt, what is the output voltage change at the regulator output? So, regulated output voltage change, that is equal to 15 millivolt into actually 50 millivolt divided by the resistance that we had used here, that is in this case it is I want to go back to, okay, it is here. I think today's circuit is somewhere here. Okay, this is R1 and this is R10. So, we have to find if this voltage changes by, if the zener voltage changes by 15 millivolt, this also have to change by 15 millivolt. That means the 50 millivolt change had to occur here. Then if you know 50 millivolt change here, then we can find what is the change here and what is the net change at V0. So, considering this, then we can recalculate R1 and R2 are the two resistors. Now, I can write 3 volt divided by R1 into R1 plus R10, that is the output voltage change in the output voltage expected, because 15 millivolt divided by R1 gives you the current change into R1 plus R10 is the resistance. So, the total resistance. So, that will be the total change in the output voltage. So, that if you work out this, that will be, because we know that this ratio is we are zener voltage is 5 volt and R1, R2 and R1 and R10 can be computed because 7 volt is what our output voltage. 7 volts equal to 5 into R1 plus R10 divided by R1, because we got 7 volt from 5 volt reference. That means this ratio you can determine. So, this ratio will be 7 volt divided by 5 volt, that is the R1 plus R10 divided by R1. So, substituting this value there, then you will get delta V0 change, that will be we can, because now we had substitute here, this is to be replaced by this 7 by 5. So, that actually comes out to be 15 millivolt into 7 by 5, that actually 21 millivolt comes. So, because of the drift in the Zener, the regulated output voltage will change by 21 millivolt. So, this is the error due to the Zener drift. If the regulated output V naught changes by 21 millivolt, then what is the expected change in the output current, that we have to calculate. That is, if you go back to the circuit that we have started today, if this voltage changes by 21 millivolt, that is what we have got because of the drift in the Zener. If this changes by 21 millivolt, then what is the change in current that is expected here? Because if this changes by 21 millivolt, then you will we have to find out what is the change that is expected at this point. Then if I know the change in voltage at this point, then I can find out what is the change in current through this. Because if you recall our earlier class values, that this is taken as a 230 ohms was the value taken, and then this was taken as a 5K. Then I had to go back and see what was the other values taken. We have taken 5K, I will calculate the values. This is 235 ohms. Actually, we have not calculated that values. Let me check whether I have calculated or not. Okay, we will write down the values first. So, this was taken as 470K. This was taken as 470K. This was taken as 470K, and this was taken as 5K. So, we had taken 2 volt difference across 5K. That means we will have then this is taken as this voltage is 5 volt. So, you got 2.5. So, this has to be minimum 2.5. So, we have 2 volt as designed for the potentiometer. So, 5K has 2 volt, that means 2.5 will be a voltage across this, then 2.5 plus 2 4.5, if it is 7 volt, then remaining 2.5 has to be across this. So, 2.5, 2.5 and 2, that is the voltage across the this point. So, 2 volt here, 2.5 here, 2.5 here, that is the normal values. So, if we go back to our circuit here, I have named them so that easy to refer. So, I call this as R3, this is 0 part as R4. So, we have to find R3, R4, that can be easily calculated. So, R voltage across R3 equal to R4 equal to 2.5 volt. R3 R4 is 2.5 volt. So, we had find R3 and R4 values, because for 2 volt for 2 volt for 5K the voltage drop is 2 volt. So, we can compute what is the required voltage for 2.5 volt, required resistance for 2.5 volt. So, R3 will be we will have 5K divided by 2 into 2.5, that comes out to be 7.5 no sorry 12.5 sorry, that will be 12.5 divided by 2, that is 6.25 K. So, we need R3 is equal to R4 6.25 K. So, R3 is equal to R4 will appear to be 6.25 K. So, our interest is that to compute the voltage change at the potentiometer point. So, if we take this potentiometer, assume that it is at the maximum, say at 20 milliampere, then we know that voltage at this point is 4.5 volt, because this is taken as 2.5, voltage across this is 2. So, voltage at this point will be 4.5. So, at that point what assume that current is 20 milliampere. So, now at 4.5 what will be the change, because if this voltage changes by 25 millivolt, that is what we have calculated, then what is the expected change at the midpoint. So, now we go back and calculate what is the expected error. So, we will get the voltage at the potentiometer end, meter top end is equal to 2.5 plus 2, that is equal to 4.5 volt. This corresponds to current of 20 milliampere. This corresponds to current of 20 milliampere. So, voltage at the potentiometer top end is 4.5 volt and the current is 20 milliampere. Now, if the 7 volt supply voltage changes by 21 millivolt, then what is the voltage change at the potentiometer top end? For delta V naught of 21 millivolt, the corresponding voltage change at the top end of the potentiometer. Top end of the potentiometer, that will be 21 into 4.5 divided by 7, that is the expected change at the top end of the potentiometer, because there is a 21 millivolt change at the regulated output voltage. So, that if you calculate this, that actually comes 3 into 4.5 millivolt, that is equal to 13.5 millivolt. We will have 13.5 millivolt change expected at the top end of the potentiometer. So, that means if the temperature of the Zener changes by 100 degree C, then the regulated voltage changes by 21 millivolt, that makes the potentiometer top end change by 13.5 millivolt. Now, we have to calculate, because of the potentiometer top end changing by 13.5 millivolt, what is the expected current change in 20 milliampere? Because if you look back, go back to the circuit and see if we go back and see this, now we arrived at the voltage change at this point is 13.5 millivolt. 13.5 millivolt, for example, if it goes up here, then 13.5 millivolt have to go up here. That will demand approximately 2 times voltage change, because there is a divider of 1 or 2. So 27 millivolt change have to occur here. If assume that this is almost close to the top, then 27 millivolt change have to occur at the resistance part here. So we name this resistance, we name this as R5. So what is the expected change at R5, assuming the this potentiometer is also at the top, that is a span potentiometer, we call this as a span potentiometer. So assuming the span potentiometer is at the top end, assuming the span pot at the top end, then voltage change at assuming the span pot at the top end, the voltage change at inverting input is equal to 13.5 millivolt, that is equal to voltage change at the non-inverting input. So the voltage change expected voltage change at the non-inverting input is 13.5 millivolt. So if the 13.5 millivolt change, that is negative input, at negative input delta V is equal to 13.5 millivolt. So voltage change across R5, that is R5 is the 235 ohm resistance, that is R5 is this 235 ohm resistance. So voltage at this point, what is the expected voltage change? That will be twice, because we have this and this voltage divided by a factor of 2. So voltage change across R5 will be twice the value. So we write voltage change at R5. Across voltage change across R5, 2 will be equal to 2 into 13.5, that is equal to 27 millivolt. Voltage change across R5 is equal to 27 millivolt. So delta current change equal to 27 divided by 230, 27 millivolt divided by 230 volts, that is 230 ohms. That actually, if you calculate, that will come almost if I take that is 27 by 230, I think it goes by 3, roughly it comes about 0.08 milliamps. So if we have 0.08 milliampere change in the 20 milliampere current, due to the drift of the zener. If the zener voltage drifts by zener drifts by 30 ppm, then you will have a output current error of current drift of 0.908 milliampere. Since the expected voltage change is plus or minus, this current change also can be plus or minus 0.08 milliampere. This is the current error expected because of the zener voltage drift. Similarly, we can calculate the error due to the change in resistance, because we are using voltage regulator. Because of the voltage regulator, if this values, these two resistors value change with temperature, then our also output voltage will change. We already discussed about this. We have said if I use, say, for example 25 ppm resistors here, one can go up, one can come down, and then we can find out what is the drift in the output voltage. So, assuming that R10 or R11 that we already calculated, we have to calculate first R1 and R10, and then we arrive at what is the expected drift. So, assuming R1 as 100K, because we can't keep low value, that low value will consume lot of current. So, let R1 be. Next we calculate the second one is calculate the current drift due to R1 comma R10 change. That is the thing that we are going to calculate. So, R1 equal to 100K. So, R10 is how much? Because we know the ratio between R1 and R10, we already done this one. So, R10 is equal to 5 divided by R1 into R1 plus R10, that is supposed to be 7 volt. So, now R1 is known, so R10 can be calculated. So, 5 by 100K 10 power 5 in 10 power 5 plus R10, that is equal to 7 volt. That is 7 volt is equal to 5 into 10 power 5, that is R1 plus R10 divided by 10 power 5. So, we had to find out now R10 in this. So, that comes 7 into 10 power 5, that actually is become 5 into 10 power 5 plus 5 into R10. That actually is subtracting there, 2 into 10 power 5 divided by 5 will become R10. That comes actually, you have 100K here, 200K, that become 200K, 210 power 3 divided by 5, that is equal to, this is R10, that is equal to 40K. So, if I assume R1 as 100K, then R10 comes as 40K. So, now we fix the drift, assuming we are used to say 50 ppm resistors, assume it can be 25 ppm or it can be 10 ppm, that depends upon what is the drift that you are looking for. Here let us assume that we have 50 ppm resistance, assume R1 drifts by R1 comma R10 drifts by 50 ppm per degree C. We have to find out what is the voltage drift. So, we have to find what is the, assuming R1 is decreasing, R10 is increasing. Assume R1 is decreasing and R10 10 is increasing with temperature. Now, you may ask why it is to be like that. It can be other way around also, that is R10 can be decreased, R1 can be increasing. It can taken both ways, but we have taken here this because both ways, one will be increasing, another case it will be decreasing, but the magnitude is same anyway. We are going to write it as plus or minus. So, that really does not matter. So, we can take R1 is decreasing, R2 is increasing. So, if you find what is the delta R change. So, delta R1, the delta R1 change would be R1 is 100 K. So, 100 K into 50 ppm into 100 degree C. So, we said it will be decreasing. So, that will be minus, delta R will be minus. So, this works out to be 10 power 4, 10 power 5, 5 into 10 power 8 100 K, because 5 into 10 power 8 divided by 10 power 6, that comes 500 ohms. That is R1 will decrease by 500 ohms. Then we can also find out what is the change in R10. So, delta R10 would be equal to same thing, because delta R and 40 K. So, they have 40 K into same 50 ppm 100 degree C, that comes 10 power 6. That is the expected change in resistance. That will be 3, 4, 20 into 2, 3, 4, 3, 10 power 7 divided by 10 power 6, that comes out to be 200 ohms. So, delta R will decrease by 500 ohms, R1 will decrease, that is in nutshell R1 will decreases by 500 ohms, then R10 increases by 200 ohms. So, if that is the case, what is the regulated voltage change? So, change in regulated voltage. Voltage change would be, now we find the new value, because we have the old formula 5 volt divided by R1 into R1 plus R10. So, now the values have changed. So, that will be 5 volt 5 into R1, which actually reduced by these things 500 ohms. So, 100 K 100 in 10 power minus 3 minus 500, that is R1. Now, plus the R10 had increased by 200 ohms. So, we have 40,200 here, that divided by 99,500, because 100 K reduced by 500 ohms, that is the new voltage. So, that is the new output voltage, new V0. That actually, if you simplify, that you get 99,500 minus plus 40,200 divided by 99,500, you will get. Now, that actually, if you calculate that, you will get 99,500 plus 40,200, that comes. So, you will get 139,700 divided by 99,500, that actually goes off. So, you will get of course into 5 is there, into 5 is there. So, if we simplify further, that comes, I write the next step. So, you will get So, you will get new V naught, new regulated voltage, that will be 35.3. I can remove this, I can simplify here itself. So, I will remove this 5, actually it comes 149, that comes 199 actually. So, I will remove this here, it will become simple now. So, that is actually become 1397 divided by 199. If we make as 200 as this, for simplicity I make this as 200, then it become 200, that comes by the net 6.985 volts. The new voltage actually the new voltage actually had become 6.985 instead of 7 volt. So, the output voltage had reduced. So, change in output voltage. .985, that is equal to 15 millivolt. So, you will get 15 millivolt change in the regulated voltage, and that 15 millivolt change again will produce a error in the current, that I am not calculating, because earlier we had done it for Zener drift of 13.5 millivolt. We have found the current drift. Now, it is instead of 13.5 millivolt, it is 15 millivolt. We had Zener drift of 15 millivolt exactly. So, Zener was drifting 15 millivolt, that 15 millivolt had given us current change of that we have calculated, not 0.08 milliamps. So, 15 millivolt change had given you the current change of not 0.08 milliampere. So, here also the same change will come. So, the voltage change, this 15 millivolt change is due to resistance drift, but the current actually will decrease now. So, the expected current change in 20 milliampere equal to in 20 milliampere is equal to 0.08 milliampere. This is same as what we have calculated in the previous case. So, this is how we have to calculate current change due to the resistance drift. Resistance drift we are considered only at the voltage regulator stage. We are not consider the resistance change in the current transmitter part. Now, we look at the other errors in the current transmitter part, because there are not much error there in the voltage regulator part, because there are only two main contributors for the voltage regulator part. There is one more error possible in the voltage regulator part, because if you look at the circuit that we are considered now, what is the error due to the Zener drift, what is error due to this and this. If because of this you got 15 millivolt change here, because of this Zener also we got 15 millivolt change. Of course, the offset voltage of this op amp can have a drift, that will also change the output voltage. So, if I use for example simple op amp like LM324, there is offset voltage drift of 15 microvolt per degree C. So, if the offset voltage drift this to be considered, then I had assume that the voltage change expected at this point is 15 microvolt per degree C. For 100 degree C, 1.5 millivolt change is expected here, then 1.5 millivolt change expected here. That will make 1.5 into the corresponding multiplication factor, around 4 millivolt change expected at the output. That will also make the current drift. So, we can now calculate what is the error due to the offset voltage drift of the op amp, due to the offset voltage drift of the op amp, that is present in the voltage regulator part of this circuit. So, next third error that we calculate would be Next third error would be error due to offset voltage change. V offset of voltage regulator part. This is the third error that we are going to calculate. So, let V offset drift is equal to 15 microvolt per DC. This is a general purpose op amp. That is the figure that we get for most of the general purpose op amp. So, for 100 degree C, total offset voltage change that will be 15 into 100 microvolt, 1.5 millivolt. So, you expect to have 1.5 millivolt change at the input of the op amp. So, then if for 1.5 millivolt change, input of the regulator op amp, the expected change at the output of the regulator is equal to 1.5 into 7 by 1.5 millivolt into 7 by 5, that is our resistance multiplication multiplication factor, that is R1 and R10 contribution, that actually comes 2.1 millivolt. So, we will have a 2.51 millivolt change at the output of the regulator due to offset voltage drift. These are the three errors possible in the voltage regulator stage. So, corresponding to 2.5 millivolt, again we have to find the current change at the output of the regulator. So, current change in the 20 milliampere output. Output will be, because we got for 0.08 milliampere for 15 millivolt. So, we can also find for 2.1 millivolt, that is this, that is the expected change. So, you get 0.16 divided by 15 millivolt, that actually comes almost 0.01 milliamps. So, offset voltage will produce a 10 microampere change at the 20 milliampere current. This is small. Nevertheless, we have to compute all the errors like this depending on what is the op amp that you are using. Now, we have finished calculating the error that is coming due to the voltage regulator part. We have not calculated the error that is expected to come due to the various changes that is that is expected in the regulator part, because if you redraw the circuit, now the regulator part alone, the current converter part, if I take the current, so we now next calculate error in the current converter stage. So, we had now look at the current converter stage to compute the errors. So, first we pick up the simple circuit here. The current converter looks like this. and the span part here, and this is the regulated voltage 7 volt which I had set. Then we had that various resistors, this is that 5K. Then we had this is given to the reference zener. This is given to 5 volt, this is 470K, 470K, this is 235 ohms. Then we had taken this voltage as 4.5, this was taken as 6.25K, this also was taken as 6.25K. So, this is our current converter stage. So, now we have to calculate what are the errors involved in this, we had to find what are the errors involved, and then we had also had to compute that error in terms of current that is flowing in this circuit. Now, if we take this circuit, first we take the simplest one, that is offset voltage drift of this operation amplifier. That is if there is because this operation amplifier also will have offset voltage drift. So, if there is offset voltage drift here, then what is the current change here? So, the offset voltage change, for example, is the same general purpose op amp if I take, we can expect it is 15 microvolt per degree C. So, for 100 degree C, we can say 1.5 millivolt change is expected here. There is offset voltage. If 1.5 millivolt change or 1.5 millivolt change here, then they also have to change 1.5 millivolt here. If 1.5 millivolt have to change here, then we know 3 millivolt have to change here. Because 1.5 millivolt change will come only if it is twice the change here, because we have 1:1 here. So, we have a 3 millivolt change expected here, that is 3 millivolt change here. Then get 3 millivolt change, 3 millivolt divided by 235 is the current change that is required. That is how we have to calculate the current change. So, essentially first to find out what is the offset voltage drift here, then same drift is expected here, then the drift, that is the voltage change that is required here, then find the voltage change here, expected voltage change here, then that once you know the expected change in voltage here, then resistance is known, the current change can be computed. So, we go step by step. So, now we are calculating offset voltage drift, error due to offset voltage drift. So, that is the first error in the current converter stage. So, error due to offset voltage drift of current converter op amp. That is the error that we are going to calculate. Offset voltage drift is equal to V offset, that is equal to 15 microvolt per degree C. So, delta total change, total offset voltage change, is equal to plus or minus 1.5 millivolt. This is coming as 15 microvolt into 100, considering 100 degree as the temperature change. That is the change expected. So, offset voltage, so expected change in the non-inverting input is 1.5 millivolt, that is equal to expected change in the inverting input. Expected change in the inverting input as well, that is also equal to 1.5 millivolt. If the 1.5 millivolt change required, then the expected change at the output resistor, that is this resistor, I name it, I think we have named it, and that is 235 ohms, I call it as R0. So, expected change in across R0. So, the expected change across R0, that is equal to 235 ohms, that is equal to okay, sorry, that is equal to expected change across R0 is equal to 1.5 into that 470 k divided by 470 k, 470 divided by 470 plus 470 k, that is equal to 3 millivolt. So, the current change, so the expected current change in 20 milliampere, that is equal to 3 millivolt divided by 230 ohms, that is equal to, if I convert into microamps, that will be 3000 divided by 230 microamps, roughly around 12 microampere current is expected to change due to the offset voltage drift of the current converter stage. So, if there is a error, there will be error of 10 microampere, that is error of 12 microampere because of the offset voltage due to the second stage. This is considerably smaller compared to the other errors. Now, let us pick up the other error, one more error, because we have now seen that offset voltage drift of this produces 3 millivolt change here, and 3 millivolt change will correspondingly produce 12 microampere current change through this. Next, let us find out what is the error due to the resistance drift. As you can consider these two resistors, this 470 k and 470 k. Now, let us name them actually. This is take it as R11 and this is R12. If R11 and R12 change with temperature, then also output current is expected to change. So, we assume one is increasing, one is decreasing, and we will also take 50 ppm drift. So, if I take this is going up by 50 ppm and this is coming down by 50 ppm. In that case, what is the main error? Now, if this voltage is 5 volt, then we know that this voltage this point voltage at this point divided by this this and this. So, if this resistance goes up and this resistance comes down, then voltage at this point will not be divided equally, because we have taken 5 volt and this is equal to this, and then we have taken the null point voltage is 2.5 and it is not going to be 2.5 volt, and this if this increases, this decreases, voltage at this point will decrease and that will decrease this current as well. So, we have to compute that error. Similarly, in our assumption earlier, we have assumed that this voltage itself increasing by 15 millivolt because the Zener voltage is by 15 millivolt, and because of that we have assumed that output voltage was changing and this 7 volt change was there, and that will change here and that will change the current here, we had assumed. But then if this increase will also increase this, and then that will also increase the current. So, that also we have to calculate, that is another error that is left out for computation. So, we have one error left, that is because of this resistance and this resistance drift. Then because of this resistance change, this voltage change, there will be a voltage change here, that also will change the current through this. And then more importantly, if this resistance changes, then if this resistance drifts with the temperature, then the volt current will change. So, that also we have to compute. Similarly, this resistance drift also will contribute for the change in voltage here, and that will also change the current. So, we have to compute all these errors. So, first we list it and then we compute it in the next class. So, the errors that is to be calculated are so the second error that is to be computed is change in current current due to Zener voltage change. Then we also have to compute change in current due to R10 R11 change. I think it is R10 and R11 and R12 change. Due to R11 R12 change. Then we also have to compute error change in current due to 235 ohm resistance change. That is I think we have named it as so these are the errors that we had to compute, that we will do it in the next class. Now, if you see this, the various error computation is very important, because if you make simply 420 milliampere and assume that the current will not change with temperature, that would be wrong. Now, this gives an idea that what is the total change in current expected, and which are the parameters which are very critical to reduce the output drift. For example, if I take the low ppm resistor, then we can expect low current change in the output. So, with this I will stop. We will continue in the next class. Thank you.